Hello, everyone. I'm Muldrow. I'm a PhD student at UMass Amherst. And today I'm going to tell you about string theory. I'm going to tell you about some of its implications for physics, so phenomenology. And I'm also going to tell you how it's related to a subject called quantum field theory, or QFT for short. Also, there's a big chance that I accidentally use jargon. So if I do so, if you don't understand anything I'm saying, or if you have any questions, please just feel free to blurt out if that's okay with the moderators. So without further ado, so the overview of this talk, I'm going to begin with some reasons why string theory is interesting, why you might want to study it. Then I'm going to tell you sort of what string theory is. I'm going to begin with a more historical idea of what string theory is, sort of the view of what string theory was in the 70s and 80s and early 90s. And then I'll discuss some more modern ideas of what string theory might be that developed in the mid-90s. And then lastly, I'll discuss some current research, so string phenomenology, so the study of what string theory does. And I'll also discuss quantum field theory, which is a subject in string theory, subject in physics that string theory has a lot to say about. So why might you want to study string theory, or why even be interested in string theory? Well, it's quantum gravity. It combines quantum mechanics and it combines gravity. And that's not an easy thing to do. A lot of people in the 20th century had sort of naive attempts to combine quantum mechanics and gravity and quantize gravity. And there were a lot of difficulties. And string theory is this completely different approach. It doesn't really start with gravity, but it starts with quantum mechanics, and gravity's a surprising output. That's one reason to study string theory. It also teaches us a lot about a subject called quantum field theory. So quantum field theory is a subject that sort of arose in an attempt to combine quantum mechanics and special relativity. Quantum field theory, sometimes I'll call it QFT, it describes very, very well 3 of the 4 fundamental forces. So it describes electrodynamics. It also it describes the strong and weak nuclear forces. And the way that this is done isn't with quantum field theory, these other theories. So string theory teaches us a lot about quantum field theory. Also, quantum field theory shows up in other contexts. So there's, of course, the quantum field theory describing the fundamental forces of our universe that I just mentioned. It also shows up, different kinds of quantum field theories show up in different subjects, like condensed matter physics. There are many different types of quantum field theories. And string theory is a profound tool in studying quantum field theories. It can give us completely different descriptions of quantum field theories, and it can allow us to discover new quantum field theories. Another reason to study string theory is it gives us new math. A lot of the Fields medals of the last 30 years, so there's no Nobel Prize in mathematics, but there's a very prestigious prize in mathematics called the Fields Medal. In the past 30 or so years, a lot of the Fields medals have been awarded to people working in subjects that are very closely related to string theory. And string theory actually has allowed new math to be discovered. There's a subject in mathematics called mirror symmetry that string theory, well, it was discovered with string theory. There are also many other subjects in mathematics that string theory is surprisingly closely connected with. One last reason to study string theory is it also might be the theory of our universe. In addition to being quantum gravity, teaching us things about quantum field theory and giving us new math, it might just be the fundamental theory of our universe. Not saying it is necessarily. It's actually kind of hard to test this with our current technology, but it might be the theory. Even if it's not the theory, it's still worth studying for these 3 reasons. But it might be the theory of our universe. I'll tell you in this talk a little bit about how people are trying, or we are trying to use string theory to make predictions about things that we can experimentally test in our lifetimes. So, what is string theory? Well, here's a historical answer. Historically, at least before the 1990s, string theory really was just the study of tiny little fundamental strings. So there's sort of a sophisticated approach to this, but roughly you have these little vibrating strings. Quantum mechanics controls the ways in which they are allowed to vibrate. If you're very far away from the string, and the string's very small, and you don't look too closely, it just looks like a little point. So it looks like a little particle. And the different ways in which the string is allowed to vibrate makes this what looks like a little particle. The string vibrates in a way that if you don't look too closely, it looks like it reproduces the various different types of particles we're very familiar with. So it reproduces particles like photons. It can reproduce particles like electrons. It can also reproduce particles that look like gravitons, which are how we expect what we expect the particle associated with gravity to be. So it's quite surprising. There's a very simple sort of explanation for what these strings are, and you combine quantum mechanics with them, and then it turns out that the vibrations of these strings just behave like particles that we're quite familiar with. It also gives us some particles that we haven't yet discovered. So that's sort of what string theory is. That's sort of the historical notion. I should also mention that there are multiple different kinds of string theories. You could have closed strings. So you go around the string and you get back to your starting point. You could also have open strings, for instance, these two, where the endpoints of the strings flail around. Also, if you have a little bit more sophisticated type of string, a string called a superstring, there's some additional boundary conditions you can have besides just being open or closed. There's some reasons why one would study these so-called superstrings. There are multiple reasons, but anyway, there's some more boundary conditions to them just besides being open or closed. So there are 5 different types of superstrings. Maybe I'll just briefly say the way you do this sort of quantum mechanics of these strings, the way you look at how quantum mechanics vibrate, how quantum mechanics affects these is as follows. So the string, as it moves through time, generates a world sheet. So remember, a particle, as it moves through time, traces out a world line. These strings trace out world sheets, and the world sheet has one time direction and one space direction. And the way you sort of quantize these strings is by doing particle physics on the string, or quantum field theory on the string. If that doesn't mean anything to you all, you can ignore what I just said. But anyway, there's a well-defined approach to quantizing these strings. And so it's a sort of solid approach to understanding how quantum mechanics allows these strings to vibrate and interact with each other and reproduce particle physics. It also reproduces, of course, or famously, it reproduces gravity. And it gives you actually Einstein's version of general relativity, quite surprisingly. You start with the strings and you don't even ask for general relativity, and it gives you that as an output.
Sorry, would you mind explaining what you mean by that?
So you start with the point about gravity.
Right. I mean, you've used this language, reproduces, like, a lot.
Yeah.
And I think for the particle case, I sort of have an understanding of what you mean. You mean the behavior is identical to that of our different species of particles with their different properties, but the gravitational case is less clear to me.
Yeah, so I guess there are multiple ways to see this. One is that these strings can vibrate just like gravitons, so the particle associated with gravity. So that's sort of a quantum gravity. what it can do. Also, if you have sort of gravitational fields that these strings are vibrating through, the string theory, it becomes mathematically inconsistent unless these background fields, unless space-time is warped in a way that is governed by Einstein equations. So string theory is only consistent with space-time satisfying Einstein's equations.
So, sorry, just to push a little bit more, would it be correct to say that it's not providing the background curvature, but it only has dynamics that are consistent if you assume that curvature is there?
Yeah, that's a good question. I would say that yeah, that's a good question. And I think the answer is slightly controversial. Maybe it shouldn't be controversial. I would say that, are you familiar with the term coherent states or?
Yes.
Yes. I think I've heard some people say stuff like it does source the background, like by creating a coherent state. Sort of the way like in quantum field theory, you can like do quantum field theory with a sort of background. I think maybe for the purpose of this talk, I'll just say that it's only consistent if the background satisfies Einstein's equations.
Thank you.
And then so if you have it, then you necessarily have Einstein's equations. And maybe you'll disagree with me saying that it predicts general relativity. I think this could be maybe more of a discussion after, or yeah, but that's an excellent question. People discuss that quite a lot. Like what backgrounds actually mean in the context of string theory. I think some people have, yeah, it's a rich discussion topic. Yeah, that's an excellent question though. So anyway, there are 5 known types of superstrings. There are 5 known types of boundary conditions that these strings can have. You see these 2 different types here, but if you allow for some extra fancy stuff on the strings, you actually get 5 different types of boundary conditions. So this is sort of what string theory looked like in the 1980s. But there were some other things that started to appear in string theory, and there were a lot of good reasons to believe that they existed. So you had these strings, but people would do various types of calculations. And all of the calculations really suggested that in string theory, there are membranes too. So a string is an example of a membrane. It's sort of if you look at a moment in time, it's a one-dimensional membrane. It has one dimension of spatial extent. But string theory, in the 90s, it really became obvious or apparent that string theory requires other kinds of membranes. And people started to work out all various properties of these membranes. So in each one of these 5 superstring theories, people started to figure out what kind of membranes were there, how they behaved, their tensions, and stuff like that. So string theory became less specifically about strings. It became a theory involving, more generally, lots of different types of membranes. There are some issues with membranes. We know how to do quantum mechanics with these strings, sort of with the way I heuristically described earlier. But it's not known how to quantize these membranes in the same way we quantize these strings. So that was an issue with string theory. Another issue with string theory is, in string theory, a lot of the calculations are perturbative. So we assume something about the strings. We assume that we pretend that they really have small tension, and then we can do calculations quite well. We have this ideal way we think things should behave, and we calculate perturbations from it. And our perturbations are under control. And that's very nice when strings don't have a lot of tension. But string theorists didn't really know what to do when strings had a lot of tension. So this historical answer of what is string theory, being these little strings, was incomplete. Also, there are other reasons to suspect incompleteness based off of, for instance, or potentially Aaron's question. So anyway, in the 80s, string theory was incomplete. So there are other things besides strings, and it's not clear what to do with them. And people could only really do calculations in certain limits of string theory, like when the strings didn't have very strong tensions. Then you could do perturbative calculations. But it wasn't clear what to do with string theory. So in the mid-90s, if someone asked, what is string theory? The answer went from looking like this to something looking more like this. So in the 90s, so at the tips of this, these are 5 different types of string theories. Don't worry too much about their names. These are their names. In the mid-90s, it became apparent that these 5 different string theories are probably just limits of a single theory that to this day, we don't currently know what it is. It's been called M theory. The way people were able to notice this is sometimes they would do a calculation in one of these string theories, say type 1 string theory. And then they would look at what happens, say, if they made the tension of the string really, really, really large. So when you do this, you can't do the perturbative calculations anymore. But you can still track some things. But what was quite remarkable is if you made the tension stronger and stronger, suddenly another string theory, another one of the 5 string theories, would be appropriate for doing calculations. And then suddenly you could do perturbative calculations in the other string theories. And this is a subject called dualities, where you can use different string theories to study the same physics. And it became clear that all of these different string theories are just different limits of a single theory. And this web of dualities is very much explored these days and used all of the time. And it's very interesting. And it's mathematically also interesting because you'll have different string theories describing things, and they'll describe the same thing in a different way. And this gives you sometimes different areas of mathematics describing the same thing. And this allows for some mathematics results. So anyway, the modern answer is that string theories, the 5 string theories we know, are just limits of a single theory called M theory. And we don't know what this M theory is, but we might figure it out. Maybe in our lifetime, maybe not in our lifetime. Maybe it will involve changing quantum mechanics or generalizing it or constricting it somehow. Anyway, so this is sort of the modern answer of what is string theory. It's less clear in some ways, but it seems like string theories are just limits of some strange non-perturbative object or theory. All right, so that's what is string theory. Another question maybe you'll ask is, suppose string theory is the theory of our universe. What does it tell us about our universe? Also, does anyone have any questions about the last slide, or maybe after the talk? I have questions about this slide. So what does string theory tell us about our universe? Let's suppose that string theory is the theory of our universe. What does it tell us about it? Well, we're also not quite sure. Well, we know some things. String theory predicts that there are strings in our universe and membranes. It also predicts extra dimensions. But we're not really sure what string theory tells us about stuff that our experiments can probe. I do want to say briefly, though, if we had not discovered gravity, let's say we lived in a weird alternative history where we hadn't discovered general relativity, I think string theory would have maybe allowed us to discover general relativity. But unfortunately, with our history, we have already discovered general relativity. So that's not a prediction by string theory. So what does string theory tell us about our universe for experiments we can do? We're not yet sure. But this is the subject of string phenomenology. People, including myself, are trying to figure out what string theory tells us about our universe. This subject is both difficult and interesting. So as I told you earlier, there are 5 different types of string theory, or 5 different string theory limits of M theory. Well, there are 5 different types of string theory. Turns out each one of these different string theories lives in 10 dimensions. If you do the math of the calculations involving these strings, it turns out that the string theory doesn't behave the way you would want it to, unless the number of space-time dimensions is 10. That's actually not, I'm okay with that. The reason I'm okay with that is you can hide 6 of the dimensions. So if we live in a 4D universe, 3 space dimensions in one time, maybe it comes from string theory, and we just 6 of the dimensions are hidden. So how does one hide dimensions? Well, this is the subject of compactification. Just briefly, if the dimensions are really small, then our experiments can't detect them. If our experiments can only probe length scales much larger than the hidden dimensions, then our experiments can't notice directly those 6 dimensions. I can give you a brief example of this sort of notion. So I have this cylinder, and the way I can hide a dimension on it is as follows. So if I have the cylinder, the surface of the cylinder is 2D. I can go up and down, and I can go around. But if the cylinder's radius is extremely small, and I don't have a good microscope, the cylinder just looks like a line segment. So this is sort of the way we can hide dimensions. In string theory, we hide 6 dimensions. Oh, I see Asher has raised a hand. Yes. Do you have a question? Oh, the hand is no longer raised. Okay, well, if you have a question, feel free to ask. So anyway, this is sort of the notion of how you hide dimensions. You can make them compact, and you just make them really small. And if you don't have a good microscope or a particle accelerator, which is a type of microscope in a way, then you can't see them. In string theory, I want to say you can't make them arbitrarily small. There is actually a minimum length called the Planck length, which is about 10 to the power of -34 or something meters. But that's a really small.
Wait, was my mic on mute before?
Oh yeah, I can hear you now.
Okay, I'm so sorry. I was technical difficulties. The question I had is, this cylinder, is it a finite cylinder? Is it?
Oh,
When I think about physics, I think about we live in 4 dimensions at most, but it's like, the universe might have some unifying shape of it, but I mean, what does it like? Can you just talk about what it means to start in a cylinder? Like,
yeah. So what I basically meant is like this cylinder here. This was a sort of toy example. Maybe it's infinitely long vertically. That's fine. What I'm saying is that like if the radius of it is sufficiently small and you don't look too closely, let's say you're walking around the cylinder or up and down, or you're just looking at the cylinder and the radius is small and you don't look at it with great resolution, it just looks one-dimensional. If the radius is small, maybe it's
okay, yeah, that makes sense. Okay, so it's I can think of this as like the world that I live in, or the world.
Yeah, the world you live in is more like this equivalent to this line here.
I see. So the world that I live in is this line. Well, it's really this cylinder, but it's just that measurements on the scale of other dimensions are hard to make.
Yeah.
Okay.
Yeah. You would need to really start to notice physics that you have directions besides just this like vertical line. You would need to make stuff with small enough wavelengths to be able to probe the cylinder. And to make stuff with small enough wavelengths, if the cylinder is like small enough radius, that the energy required to make stuff with small enough wavelengths is just gets larger and larger. And if you can't access those high energies, then you just won't be able to immediately access or probe that cylinder.
Okay,
unless
yeah,
you-
thank you. I have another question. I'll just post it in the chat so you like I don't forget it.
Sure. I see. Okay, a comment. I think it's not a comment. I think it's or not a question in the comments section. I think it's just, yeah, it's not a question. All right, so we just hide away 6 of the 10 dimensions. This is not very mathematically difficult to do. And it's consistent with our maybe observations, because we only have 40 physics. You know, you can't say that these, or unless you can do an experiment to small energies, this hasn't been ruled out. So anyway, the way to get to 40 theories in string theory is to hide these 6 dimensions. Unfortunately, there are lots of ways to hide 6 dimensions. Okay, I'll maybe answer that question later. Or I think Asher, you said I could answer that question later. Anyway, there are lots of ways to hide 6 dimensions. Of course, in all these ways, you're making the dimensions really small, but there are lots of different shapes. So in this case, the small dimension is a circle. So like this around direction is a circle. But more generally, if you're hiding 6 dimensions, you can have a lot more shapes, a lot more 6-dimensional shapes than just circles. So sometimes you'll hear the number 10 to the 500, or sometimes in worse situations, you'll hear the number 10 to the 272,000 different ways to hide these 6 dimensions. There are lots of ways to do it. In fact, it's almost, currently we don't know which way to get our universe, and there are too many ways currently to check to find out which one. So it's really hard to figure out which one of these shapes gives us our universe. So it's hard to tell which string theory describes our universe and what shape we're using to hide 6 of these dimensions. So some people are working on this. Some people might actually find out which shape gives us precisely our universe, though. I want to be clear. People in the 90s had a lot more optimism about this, I think. 90s and 2000s. There was even a lot more optimism in the 80s. But nowadays, people are sort of pessimistic because there are just too many ways to really, it's too difficult mathematics to find out which way is our universe. Although people are working on it, I should say that this might change, but it's not clear when or if it will change. I actually know of one Reed College person working on this, on finding the ways. So in the meantime, instead of trying to find out specifically which way we can hide 6 of the 10 dimensions, we can look at universal things that happen when you wrap up 10 dimensions, or sorry, wrap up 6 dimensions, or wrap up various dimensions. If string theory describes our universe, and you have something that always holds when you hide 6 or several dimensions, then that property should apply to our universe. And if you can find a very constraining list of properties, then you can make predictions using string theory about our universe. So this is the goal of the Swampland program, finding these universal properties of theories that come from string theory and wrapping up dimensions. So the goal here is maybe you'll have theories that come from wrapping up dimensions in string theory. So this is called the landscape. And then maybe you could have hypothetical theories that can't come from string theory. And so the goal is to try to figure out what properties of theories put the theory in the swampland. If you can find a really constraining list of properties, or or a very common list of properties that put theories in the swampland, not many theories then survive and remain in the landscape. And then the goal, or hopefully you can start to make predictions about our universe by this sort of logic. So I'm going to take a sip of water. Any questions about this? I'll go through some example. I say chat. Okay. A comment about string theory's application to describe vortices in superfluid helium. Cool. Okay, so anyway, so the swampland program, just to summarize, is you try to find some properties that always hold in every theory that comes from string theory, in every theory you get by hiding several dimensions. And if you have a list of properties that are necessary, if that list of properties that are necessary is very constraining, then you can constrain things that we would measure in our universe and then maybe make predictions about experiments. So that's the goal of this swampland program. So there are several different places where people are doing calculations, or we are doing calculations. In string theory, there's a really refined notion of what a parameter is. So like you have various things in a particular theory. You have strings, they have tensions. You have particles, they have masses. You have various interactions, and they have interaction strengths. And all of these things are controlled by parameters. And in string theory, there's a very refined notion of what a parameter is. It's actually, to maybe use technical terms, it's actually a vacuum expectation value of a scalar field, to use a technical term that maybe means something to some of you all. And actually, the space of parameters is actually a shape. It's actually what mathematicians would call a manifold, and it has some nice geometry to it. You have various lengths, and it has interesting shapes, and it's very connected to the physics in a rich way. So this parameter space is called moduli space, and much work is done in connecting this space of parameters with the types of membranes you have, the types of particles you have, and how they interact. And actually, there's been quite a lot of progress on this. There's some quite remarkable constraints about the shapes of these moduli spaces and the relationships with particles and membranes. So this is one area in which multiple conjectures have been made. There's some conjectures that about what happens when you make one of these parameters an extreme value, which maybe happens in our universe. We have the cosmological constant in our universe, which is controlling how the universe is expanding. And it's an extremely small value. And we might be able to, there are all these conjectures about these parameter spaces in string theory for what happens when you make the parameters take extreme values. There are all these conjectures of things that happen. And there's some hope that maybe the masses of neutrinos are related to the cosmological constant. So that's one thing. There's another conjecture or guess of something that holds universally in all of these different string theories. And when you wrap up dimensions, it's called the weak gravity conjecture. It's believed that in all of these different theories, gravity is always the weakest force. We observe that in our universe, but there are some more refined notions of what saying gravity is the weakest force means. One version is saying that all black holes can decay. So Stephen Hawking in the 20th century did some calculations that suggested that black holes are not black, that they actually glow a little bit, and they emit radiation. And as they emit radiation, they lose energy and then get smaller and smaller and evaporate away. In string theory, the weak gravity conjecture requires this can happen. And that actually, requiring that this can happen, actually is a requiring that this could happen for every type of black hole you could have. You can have black holes. You can also charge them up. You can put electric charge in them, for instance. Requiring that every type of black hole can decay actually is quite a strong requirement. So it forces you to have various types of particles with large enough charge to mass ratios, for instance. Also, requiring that black holes can decay controls what type of things are conserved. You can't have a conserved quantity that prohibits a black hole from decaying. And so this has implications for the type of symmetries you can have. Right, symmetries are very related to conserved quantities, typically explained in a classical mechanics class or electrodynamics class. So saying that black holes can decay and there aren't conserved quantities that stop this is very closely related with the type of symmetries that are allowed. And so actually the weak gravity conjecture prohibits a lot of kind of symmetries you might think you would have. For instance, it prohibits some symmetries that people think, or conserved quantities that people think apply, some people think apply to our universe. So some people think that the number of protons in our universe is a conserved quantity. String theory requires that it's not a conserved quantity, that potentially protons can decay, for instance. So this is one area in which string theory might make predictions about our universe. So you have these various conjectures for theories that come from string theory, and people are trying to really, myself included, are trying to sharpen these conjectures and make them stronger and stronger, and then eventually so restrictive that they restrict future experiments. Lastly, I want to say a little bit about string theory and quantum field theory. So quantum field theory is how you combine relativity and quantum mechanics, but you can do other things too. People in the subject of condensed matter study quantum field theories too. Quantum field theory is now sort of a very general notion. It turns out that string theory tells us a lot about quantum field theories. String theory has allowed us to discover new quantum field theories. And some of these quantum field theories are actually quite exotic. This work is actually suggesting that our notion of what quantum field theory maybe should change. Often the way this works is, well, this is one way in which it works, is through a subject called holography. You'll have a string theory in an appropriate container is equivalent to a quantum field theory on the boundary of this container. So string theory is kind of like a hologram. And so you can do a calculation with string theory, or equivalently, you could do a calculation in the quantum field theory on the boundary. This is sometimes called ADS-CFT, or that's an example of this. But you can then construct different string theories and then generate various different quantum field theories. Some of the quantum field theories, I'm going to skip this picture. I'm running out of time to explain it. But some of the quantum field theories are quantum field theories we know and love. And then string theory through this process has also allowed us to discover some new quantum field theories. For instance, there's a type, I won't tell you what this means, but it's called a 40 n = 3 SCFT. This is a new type of quantum field theory that was discovered by string theory in 2016. It's a very crazy type of quantum field theory. You don't have a Lagrangian to describe it. It's very strongly coupled. Actually, sort of famously in Steven Weinberg's quantum field theory textbook, he shows that if you have a Lagrangian quantum field theory, that this particular one doesn't exist. But string theory was used to discover it, the non-Lagrangian version. Oh, Ion, you have a question.
So if you don't have a Lagrangian, what mathematical object do you use as something to describe the theory?
Well, you still have things like correlation functions. So you could still do calculations like that. You still maybe have an abstract path integral, but you don't have this sort of usual way of using a Lagrangian to generate the path integral.
Okay. Thank you.
Yeah. So like a Lagrangian turns out not to be exactly necessary for making statements about observables. It turns out that Lagrangians like are almost always used in studying observables, but turns out they're not actually necessary. And this is a type of quantum field theory that doesn't use a Lagrangian. And most of the time when people think of quantum field theory, they think in terms of Lagrangians. But the existence of these types of weird non-Lagrangian theories does suggest that maybe the notion of quantum field theory needs to be changed. All right, so in summary, I'll summarize the remaining questions. So one question is, what is string theory? There are 5 different string theories where we know how to do perturbative calculations. And it looks like these 5 different string theories are part of some mega theory, but it's not known how to do calculations or how to do everything in that grand large theory. So likely string theory needs to be, it needs a definition. Someone needs to discover what it really is or what it is just limiting cases of. Another question is, what does string theory say about our universe? I discussed that a little bit in this talk. It definitely says things about very small length scales, definitely makes predictions about what would happen near the Planck length, but it's not clear what string theory says about energy scales that our current experiments can access. But that might change. People might, it's really just because string theory is too difficult right now. It could be that string theory actually makes very strong predictions about our experiments. It's just we're not good enough at string theory to figure out what those predictions are. Also, I didn't really discuss it that much, but a lot of math comes from string theory. Math has been discovered with string theory, and I really expect in the next 100 years there to be a lot more math that comes from string theory. Often in string theory, there are different ways to get exactly the same physics. There are dualities, and this gives you different mathematical objects that become equivalent by giving you the same physics. And this is quite a profound aspect of string theory. And so I think a lot of math will come from string theory. I also think that if physicists hadn't discovered string theory, mathematicians in the 22nd century maybe would have discovered string theory. Or maybe they would have taken them till the 23rd century. All right, thank you.
Muldrow, thank you very much. This was really good. This is Eris. I have kind of a very quick general question in terms of you've kept this at a level without putting everything except one equation up there. But is mathematical methods, is it mostly still pencil and paper, or computer techniques helping?
Yeah, that's a good question. So the calculations I do are mostly pencil and paper. But there are some people who do very fancy computer calculations. But I would say most of the people I interact with, it's just pencil and paper.
I was thinking when you try to apply it to something that's actually going on in the universe, that at some point you're actually trying to quantify and maybe add some numbers in, and then computer calculations may be of some help.
So I have sometimes used computers. So I've done some calculations for looking at how string theory could affect a certain type of black hole. Yeah. And there, like, I have to deal with Einstein's equations, and they're horrible and nonlinear, and there are all these indices to keep track of. And so in those sorts of calculations, and there are also some nasty integrals. And in those calculations, I have used computers, but most of my work is actually just pencil and paper. There are some people, though, who want to look at tons of different examples of hiding 6 dimensions or so, say, and they want to analyze many different examples all at once, and they'll use computers or they'll use machine learning. And but yeah.
Okay, thank you.
Yeah, thanks. Nice question. Oh, I see in the chat. Oh, thanks.
Perhaps we could return to Asher's question.
Oh yeah.
So
Oh yeah.
yeah, numerical
So-
predictions for what scale we would need to probe. What
Yeah.
ways do we need to potentially detect this? Are there any bounds?
Yeah, there are bounds. Well, I have good news and I have bad news. The good news is that there do exist bounds. So there's a minimum length scale. There's the Planck length. We know that string theory has got to be like, makes lots of the extra dimensions are larger than the Planck scale. So that's the good news. There is a minimum length. We can't just, maybe 1,000 years from now, someone will do an experiment, not find strings, and we'll just say, oh, look smaller. And then they'll look half the length 1,000 years later. And then we'll just say, look smaller. That can't go on forever. There is a minimum length. That's the good news. And the bad news is the smallest length is about 10 to the power of negative 34 meters, which is extraordinarily small and out of range of experiments. But it's possible that extra dimensions or stringy objects will occur at much larger length scales than 10 to the power of negative 34 meters. But we don't know quite what that value would be. Some people have guessed. I'm not holding my breath, though, that it will be. I don't know that we'll get lucky. We might get lucky, though. And who knows, maybe there'll be a way where we can indirectly observe or test these, look into these extra dimensions. There might be some surprising things. Maybe we won't just need to keep building larger and larger particle accelerators. Maybe we'll come up with some clever ways to probe these small lengths. But I don't know what, I guess, the smallest energy will be to probe these lengths, or the largest length scale. I just know that there is a minimum length scale or maximum energy that these effects would occur before.
Anybody else have any questions for Muldrow? I'm curious, Muldrow, what classes you took at Reed or experiences that you had while you were at Reed that led you in this direction of academics?
Oh, well, there were Joel's classes. Well, I don't want to name one person because then I feel like I have to name everyone.
You
but
could just name the class.
Yeah, I mean, Joel Franklin's classes were very relevant for this kind of work. So like there was electrodynamics and general relativity at Reed, and those classes are really used a lot. Or the material from those classes are used a lot. Also the material from quantum mechanics class. Something that's kind of fun about string theory is that it seems like it uses material from almost every class. Maybe not experimental classes, but it also uses a lot of stuff from math classes. Yeah.
It's like Zach has a question.
Oh yeah.
I'm happy to read them to you, or you can read them yourself. What's your preference?
You can read it, or I can. Any thoughts on if string theory has been applied as a model to explain, I don't know how that's pronounced. Well, the object passing through our solar system in 2017. I can definitely say that string theory has not been applied to this object. This is like an object that passed through the solar system, really. No, string theory has not been used to think about this. This is the subject of maybe astrophysics.
I have a question.
Sure. Yeah,
So,
thanks.
okay, so I don't so right now, right, I'm studying as like a condensed matter theorist, and I'm thinking of, as there are lots of contribution that Q of T and string theory has kind of given to condensed matter. Has there sort of been any has there been any sort of like, okay, I'm just gonna say what I'm thinking of specifically are stuff like quark gluon plasma or something that involves lots and lots of elementary particle in like a very small space, because to me that reminds me very much of a condensed matter system. Now, if you can use string theory to, if string theory purpose is to essentially describe uh, like elementary particles, is there sort of like another way to hybridize, say, string and condensed matter to apply to objects like quark gluon plasma? Sorry, this
Sorry.
is very out there.
Are you asking whether string theory can be useful in studying quark gluon plasmas?
Yeah, I guess. Sure.
I don't know. I know that string theory can be useful in studying other things that are not immediately string theory. There was a comment by Michael Fitzsimmons, for instance, string theory can be used to describe vortices in superfluid helium. I don't know anything about that, actually. But I've heard people talk about using string theory to study things that string theory doesn't seem like it immediately should describe or have anything to do with. Actually, string theory sort of originated by something that later turned out string theory is not the appropriate thing. So people were doing
it was strong force, right?
Quarks. What was that? Quarks.
Yeah, I was gonna say it was, yeah, strong force stuff.
Yeah, the strong force. And I think some people started thinking that maybe string theory would be what would describe this, some sort of hadronic physics. And it turned out string theory wasn't right. String theory required extra dimensions and gave you stuff like gravity, and string theory wasn't right. It turned out QCD was the correct subject for that. But like string theory has this weird origin that's not at all what string theory is used for now. And string theory does find itself like having strange applications to other subjects. But I don't work on that, and I don't really know much about how string theory is used in other subjects. Oh yes, Aaron has raised their hand.
Yeah, hi. So thanks for this great talk. So can you help us understand like what are your goals? I think we get now, why string theory is promising and interesting or fun to play with, but what motivates you in particular, and what do you hope to do?
Yeah, so thanks. Yeah, that's a nice question. Yeah, what are my goals? Well, I got a postdoc. But no, seriously, what are my like long-term goals in string theory? I mean, one goal is I want a non-perturbative definition of string theory. Like I deal with all these kinds of string theory calculations that are perturbative, and I track stuff when string theory goes into non-perturbative regimes. But I really don't, I can do calculations where I know how to track things, but I don't know quite really what the fundamental theory is that's going on. I don't know the non-perturbative definition of string theory. Another thing I'd really like to better understand is, well, we have all of these conjectures about what string theory does when you hide dimensions or compactify, or you make various dimensions really small. We have all kinds of conjectures. I told you a little bit about the weak gravity conjecture. I told you a little bit about the parameter space. And they're all these really diverse conjectures that really are unrelated to each other. And what I'm interested in and work on is making these conjectures more precise. A lot of the time, these conjectures are very hand-wavy and say, oh, when you do this, then this happens sort of this way. But they sort of use squiggly lines. They'll say, okay, this thing exponentially depends on this other thing, but they won't give you the exact number in the exponent. So I'm interested in finding those exact numbers. I'm also interested in combining all of these conjectures, seeing whether they're making them stronger or seeing whether they're actually part of like grander single conjectures. So my immediate interests are more in that kind of thing. I'm also interested in maybe longer term trying to make string theory, make predictions about our world, but I'm happy with this sort of more humble subject of just looking at these specific conjectures and trying to sharpen and merge them and maybe come up with new ones. Another thing that's quite interesting maybe is these conjectures often require some mathematics to hold. And I think that these sort of conjectures about what happens and theories that come from string theory, I think that they might allow for new discoveries in mathematics too, that maybe started with these string theory questions, but find their way in mathematics departments. Lastly, I'm also interested in just using string theory to better understand quantum field theories and be able to more generally construct them and probe the like close relationship string theory has with quantum field theories. Yes, Ian, you raised your hand again. Or did that answer your question, Aaron? Or I guess it was an open-ended question.
Yeah, it's up to you. I enjoyed it. Thanks. Good luck.
Oh, cool. Yeah, thanks. Oh, Ian, yes.
Yeah, regarding those, I think you mentioned a Q of T that doesn't have Lagrangians, right?
Yeah.
Are those necessarily non-perturbative? Or can you have perturbative Q of T that also doesn't have Lagrangians?
That's a really good question.
Or like, I guess conversely, well, not exactly conversely, but okay, from my understanding, every Q of T that has a Lagrangian is necessarily perturbative, right?
Maybe, or if it like if perturbation theory was like less valid, then maybe your Lagrangian would be less trustworthy, or but like is every theory that's like perturbative necessarily a Lagrangian theory? I don't know. That's a good question. I'm tempted to say yes, but like I'm tempted to say that if you had sort of perturbative theory, you could then just like look at the path integral and it would be also maybe weakly coupled, and then you could see how things slowly move in time, and then you could just sort of tell what the Lagrangian or action was from the path integral. That's a good question. I'm not 100% sure I know the answer to it. Oh, okay. A publication that discusses cosmology and superfluids. Superfluid helium. Cool. Yeah, I'm not sure whether yeah, I think what I've seen is every non-Lagrangian theory is just very, very strongly coupled. And are you talking or or on mute or? Yeah, that's a good question. Any other questions? Oh, something in the column. Okay. Michael Fitzsimmons writes, I wonder whether imaging vortices in superfluid helium, e.g. with helium exomers, could provide a training set for machine learning algorithms to say something about string theory. Oh, I don't know, maybe. I know very little about superfluid helium. Yeah, maybe. I guess some of the issues, one thing I could imagine is maybe you have some sort of condensed matter thing that behaves like string theory. It could be that could provide inspiration for figuring out what the non-perturbative notion of string theory is. That might be a possible thing that could happen. Sometimes you can yeah, sometimes you can maybe get intuition about something going on in high energy theory by looking at a maybe analogous thing in condensed matter physics and seeing, you might push the limitations of your understanding in high energy theory and not know what to do, but you might do the same thing in condensed matter and see what happens. And that can lead inspiration to what happens in high energy theory. Oh, Ion, you raised your hand again.
Yeah, this is actually to add to that question that was asked earlier. I think this paper is talking about a different kind of string, because the string and string theories are not the same as, say, cosmological strings, which are kind of like a topological object.
Oh, okay, yeah, I should, yeah, yeah, I guess there are multiple different types of strings, right? They're fundamental strings that I've been mainly talking about in this talk, but there are other kinds of strings like cosmological strings or topological defects or domain walls. And okay, skyrmions, a good example of something predicted by a particle physicist and is now ubiquitous in field of condensed matter physics, topological protection of magnetism, and so on. Oh, also Michael Fitzsimmons, feel free to talk into the chat if you wish, or you can keep typing your comments. I'm guessing you're a condensed matter physicist based off of these examples.
Michael, it sounds like you might be a good candidate for another talk.
Yeah.
Yeah, but actually,
sorry, I work for the government now, so can't do that.
Oh, yeah.
I see.
yeah, I was going to Muldrow, maybe you can clarify whether like string theory, the strings in string theory, whether they have any kind of strong connection to topological objects, like cosmological strings.
Oh, they
But
do have
because
a lot of connections with topological objects. To do that connection justice could be the subject of like a month of talks. But yeah, so I mean, one example in which they're connected with topological objects is, I told you briefly about holography. So I told you that string theory inside of a container is equivalent to a quantum field theory on the boundary of the container. Now, quantum field theories can have topological objects in them. And one way in which string theory can give you the topological objects of the boundary of this container is by like maybe endpoints of strings going to the boundary of this container. And that'll correspond in the quantum field theory as a topological object. For instance, that would be a Wilson line, if that means something to you, or an 't Hooft or a Dion line, for instance. But you can have various types of membranes inside of this bulk get pushed to the boundary, and then they can become topological objects. That's one example. So you can get tons of topological objects from string theory. And yeah, the connection between topological objects and string theory is really quite rich. If anyone has any basic questions, feel free also to ask, of course. And I'm also, you can reach me, you can find my email address easily. Yeah, I enjoy talking about string theory or answering questions. So please feel free to reach out, even if you think it's a silly question. Or
Well, Muldrow, thanks again. I think this was really, really very, very instructive. Somewhere along the line, we need to see some of these terrible equations that you work with, but overall was really good. So again, thanks so much for doing this, and yeah, we keep contact. I'm going to have to sign off here shortly as well, but Amy, I don't know what your plans are, but usually we kind of wind this up about now. So we don't want to
Yeah.
wear out our welcome with anybody.
Yeah, I mean, if there's people who want to chat maybe for the next 5 minutes, that's fine, but I will need to sign off pretty soon.
Yeah, cool.
Thank you so much, Muldrow. This was really fascinating, and I really appreciate you reaching out to us after Professor Franklin's talk, and letting us know, hey, I'd like to give a talk. And if any of you are feeling like it, we would love to have you come and talk to us about what you study or what you do for your work.
Is there a listserv that we can join to get notified of future talks?
Yes, I wasn't sure if everyone here was already part of that listserv. Let me send you I'll post the link in the chat bar for the sign up form for our listserv.
Well,
Right.
thank you all for organizing, and thanks everyone else for attending.
Okay, yeah. Again, Muldrow, thanks. It was really great. It was very easy to listen to, so I enjoyed
Okay,
it.
glad.
Thank you.
Yeah, I did. Great. Well, thanks.
Yeah,
Mhm.
thank you. I didn't know anything about string theory or very little, so I was glad to listen to the talk.
Yeah, I'm very impressed you managed to talk about string theory while avoiding a lot of math.
Yeah, I actually had a version of this talk at first, where I had some nasty equations, but I was worried that that might scare or make people tune out or something. There are nasty equations. You can look up maybe my papers or string theory papers if you want to see the scary equations, or you could pull up a textbook. They're not that scary when you get to know them, but well, some of them are actually always scary, but the good ones aren't that scary when you get to know them.